Hello everyone. In this video, we will take a look at gradient descent method applied to an unconstrained convex optimization problem. Let us begin by providing the problem formulation. We consider a simple setting where there are no constraints. The problem can be written as x star is equal to arg min over x f of x. In the previous videos, we did talk a lot about the domain of a function and the different requirements, that is, its relative interior be non-empty, etc. All that will actually be important. However, in order to develop an understanding, it is always important to look at the simplest case you can imagine and then slowly build upon it. So for now, we will assume that domain of f is the entire vector space V. For instance, anything involving a norm would have an unrestricted domain, because if you remember, it is required for the norm to be defined everywhere. This kind of problem is not uncommon. In fact, a routine example is the least squares problem, which is min over x in Rn, norm of ax minus b square, where b is some m cross 1 vector. Since x star is the optimal solution of this problem, the optimal value is given by f of x star, and it holds that f of x star is less than equal to f of x. So we have written down all the key aspects of the problem formulation. Next, let us make some assumptions. It is always important to think about what your assumptions are prior to analyzing, so that your thought process remains clear. Even before deciding what the properties x star will have, some assumptions regarding f are needed. In this and the next few lectures, we will be working with two key assumptions. The first assumption, A1, is that the function f is convex, and the second assumption, A2, is that the function f is L smooth. So for the next few lectures, we will be assuming that the function f is smooth and convex. There are some implicit assumptions as well. We have already said that we will always consider f to be proper closed. So we need not state that again and again. Whenever we are talking about an algorithm, you can assume that the function being minimized is proper closed. The smoothness assumption means that f is also differentiable. So the optimality condition for the unconstrained minimization problem is given by gradient of f of x star is equal to 0. Finally, when we are looking at iterative algorithms, they usually start at some initial point x1 and generate iterates x2, x3 and so on. So we need the following assumption, which is that b is equal to norm of x1 minus x star square. Though in practice, any upper bound on b suffices, since we don't actually know x star. So in summary, we have two problem parameters, L and B. The oracle complexity bounds of gradient descent will be in terms of these two parameters, L and B, as well as the optimality threshold epsilon. Let us introduce a specific class of algorithms, descent algorithms. These are those where the function value decreases at every iteration. That is, if the iterates generated by the algorithm are x1, x2, x3 till xt, then it holds that f of xt plus 1 is less than equal to f of xt for all t between 1 and capital T. An example of this kind of algorithm is the gradient descent. But note that there are optimization algorithms that are not descent algorithms. To see the property in more detail, consider also the idea of descent direction. We say that the direction dt is a descent direction if it satisfies limit epsilon tends to 0, f of xt plus epsilon dt minus f of xt divided by epsilon. This whole quantity is less than 0. We say that dt is a descent direction if by moving in that direction by a minuscule amount, the function value decreases. Now what is the quantity on the left? If you recall your first year calculus, you would remember that this is given by inner product of gradient f of xt comma dt, which is nothing but the directional gradient of f along dt. So in other words, the descent direction is one that makes the function value decrease, and from calculus we can see that it is also the one that makes an obtuse angle with the gradient. We come to a class of algorithms that use the descent direction dt so that the function value decreases in that direction. The updates in such algorithms take the form x of t plus 1 equal to x of t plus eta t times dt, where dt is the direction and eta t is the step size along that direction. One point that you can observe here is that even if dt is a descent direction, it is not necessary that f of xt plus 1 be less than f of xt. So why is that? If you look carefully at the definition of the descent direction, you can see that the descent property is valid only if we go a very minuscule amount in that direction. In practice, however, we cannot do that. The step size cannot be very small, or else there will be hardly any progress in a single iteration, and therefore you would be needing lots of iterations. So instead, we take a larger step size. But if we do that, even if we are going in the descent direction, the step size could be too large. That is, I might end up increasing the function value. In summary, we may strive to go towards the descent direction, but that is not the end of the story, because we still have to decide how much to go in that direction. And if step length is not chosen properly, we might either not make enough progress or end up at a higher function value. Next, let us look at the direction taken by the gradient descent algorithm. To see that, we first try to find out the direction that will cause the maximal decrement in the function value, ignoring eta for the time being. Since the descent is given by inner product of gradient fxt, dt, this quantity can be made as negative as possible if we choose dt in the direction of minus gradient f of xt. Of course, we would have to select the step length properly, but the negative gradient direction is the direction of steepest descent, and this is the direction used in the gradient descent algorithm. So xt plus 1 equal to xt minus eta t times gradient of f of xt, where eta t is the step size. Note that this is not the only direction or the most obvious choice. If you are in Rn, then another possible direction is minus p times gradient of f of xt, where p is a positive definite matrix. Recall that multiplication with a positive definite matrix amounts to rotation and scaling. So this direction is a rotated and scaled version of the steepest descent direction. But since p is a positive definite matrix, the rotation and scaling is such that the inner product of gradient of f of xt with dt is still negative. Let us also see the gradient descent in action, specifically at a contour plot illustrating the idea. A contour plot is really a representation of the function in 2 dimensions, with the contour lines depicting the level curves of the function. The set defined as s of alpha equal to all x such that f of x is less than equal to alpha is called a level set. A contour plot is basically a 2D plot that shows the boundaries of such level sets for different values of alpha. Let us look at a contour plot. So you can see here that if we set alpha equal to 0.1, then the line marked 0.1 is actually the boundary of the set. Likewise, the marks 0.2, 0.3, etc. show the function value along those curves. Let us say that at a current iteration t, we are at a given point x of t. Note that in general, the gradient does not necessarily point towards the optimum. It is only pointing in the direction of steepest descent at xt. So as you can see, starting at xt, we will take a direction along the negative gradient. But that of course does not point towards the optimum. So we have to be careful in selecting a small step. At the next iteration, the direction is different, and the same thing continues. As we get closer to the optimum, the progress becomes slower since the gradient sizes are going down. Further, the gradient points more and more towards the optimum. So what would happen if the step sizes are too large or too small? In that case, the convergence suffers. Small step sizes result in very slow progress, and the large ones exhibit zigzag behavior, or they even diverge. In fact, the effect is more pronounced if the function is skewed in one direction. Let us see one example where the contour lines are these very elongated ellipses. In that case, you can see that if we choose the step size just right, then we have convergence in a reasonable number of iterations. The value of eta is equal to 0.05 in this case. But if the step size is too small, that is, it is 0.01 in this figure, the number of iterations required is extremely large. On the other hand, if the step sizes are even slightly larger than 0.05, so if I kept the step sizes as 0.067, the algorithm oscillates a lot and just starts to diverge. In fact, in this particular example, I observed that if eta was 0.066, then it converged, but at 0.067, it was diverging. We are now ready to theoretically analyze the gradient descent algorithm. I will point out that if you have seen any proofs of optimization algorithms, at times they might have appeared to be opaque to you. In this course, we will try to outline the structure of the proof carefully. I will divide most of the proofs in 3 to 4 steps, and each step will involve the application of one property or one trick. For the most part, we will be deriving the results for inner product spaces only. Although for most of the algorithms, generalized versions for arbitrary normed spaces do exist, and they are also quite useful in a number of settings, but their analysis is more involved. In the assignment, for instance, we will see one generalized version of the gradient descent. However, we will focus on inner product spaces initially in the lectures so that we do not get caught up with too many details right at the start. The idea is that with your knowledge of the properties of normed spaces, you should be able to generalize most of these algorithms. So that is all for this video. We will look at the oracle complexity of the gradient descent in the next video.